Okay, let me share the screen. You're able to see the value numbering?
Yes.
All right. So folks, welcome back. I guess we finished the in the last lecture um, um, basic ideas about SCCP, and wanted you to review the algorithms and then solve the problems. So hope everybody is on track there. The homework is due tomorrow. If you have any questions, you can talk to me in office hours. And the last topic of our SSA related discussion is value numbering. And we saw how basic value numbering takes place last time, which is very interesting. It is able to do a lot of different stuff like do constant propagation, constant then the removal of redundant expressions, not only lexically identical, but in terms of value being identical, which is the biggest reason for doing it. And this was the algorithm that we saw last time with the example and so on. And so this takes care of the redundancy removal using the temporary name which is assigned to the expression, and carries out the value number. And this was, of course, limited to a basic block. And then there are several issues with it, which I won't get into it because of the assignment of the values and so on. We are going to look at a SSA-based formulation in which the value is not killed because of the assignment, and so it is always available. And in a basic block, of course, it's very easy because the value is generated and is always available within that block. So the example that is shown here in the end of this option 3, let's focus on that. We have a x plus y generated there. And although the z was reassigned, you can see here in the original program, the value could have died there because of z's reassignment, and we would not have been able to therefore substitute a redundant expression using z, because now it is holding a different value w. And so you can see that originally z was equal to x plus y, then z was assigned, and v was equal to x plus y. But since z was reassigned, we would have lost the value of x plus y in the original form, and that creates problems in terms of redundancy removal, but not in the SSA form, which is shown in the option 3. That value is held in C1 and is therefore substituted at V0 in terms of Z1. So the second value, which is Z equal to W, is of course Z2. So SSA takes care of these kinds of problems which were there originally with the value numbering, even within a basic block. And outside of basic block, it does address these issues also, and even more of the issues that are there with the value numbering. And we'll look at those as we do the global value numbering. This is local value numbering, which is inside a basic block. And even there, SSA as we are seeing here. But outside of basic block also, of course, it is even more value, and we'll see what the value is. So we'll skip this other issues about local value numbering because they're all irrelevant in terms of SSA. I'll let you read it. Constant propagation, etc., is very nicely carried out. In terms of the value numbering and doing this. The second scheme, which is so the basic block oriented scheme is relatively narrow in terms of its scope. However, the next extension is extended basic block, which we call as super local value numbering. And so what we have here is an extended basic block, and the scheme is exactly the same. It starts at the top level basic block, the root of this EBB, and it continues through this and then goes down to one of the nodes, uses the value numbering context for doing the value numbering, the table, and then repeats that for the other using the original context. Let me get into some level of details for this scheme, extended EBB or super local value numbering, and how it works. And then we'll go to the global value numbering, which is the for the whole function or the procedure. How do we do this, especially using the SSA form? So, let's look at the super local value numbering for a minute. And okay. So first of all, I think we never did a formal definition of EBB. So let's start with what the EBB is. I'm sure you probably have seen this earlier. At least in 40-40 we have done that. But if you haven't, then basically here is the EBB. So the way extended basic block looks is basically a structure in which there is no join. It's a maximal structure in which there is no join. So the way we will start generating an extended basic block is start with a given basic block. Go to its, so let's say this is my B1. And I will go to its successor, let's say B2. And for that successor, I will make sure that I have a unique predecessor, which is B1. So in other words, if B2 has another predecessor, then I will not admit B2 into the extended basic block of B1. So in this case, of course, we don't have it this side. So we'll verify that it is a unique predecessor. We'll start with B1, go to its successor. For that, we'll find out its unique predecessor. And then we'll put this into the work list. We'll go to yet another successor of B1, verify that it is a unique predecessor. If it is not a unique predecessor, let's say there is another one, which means there is a join here, we will not admit it. But in this case, both B2 and B3 will be admitted into the work list. And then what we'll do is we'll take up one of the blocks, let's say from the work list B2, and then go to its successor, which happens to be B4 here, and then check if that has a unique predecessor, which is B2. In this particular case, no, it has another predecessor, which is B3. So that's why I will not admit B4 into the extended basic block, and we will not do anything. B2 has only one successor. If it had another one, let's say like this, and that was not really how should I say, that was satisfying the unique predecessor requirement. Let's say this is B5. Then what I would have done is I would have inserted B5. I will admit it first of all into the basic block. So far, extended basic block has all these elements which satisfied the unique predecessor requirement, and they were admitted, and then by processing B2s and its successors, rejecting B4 because it didn't satisfy the extended basic block unique predecessor requirement, I went and checked the next one, which is a successor of B2, B5. That satisfied, I admitted it into the current structure and I put it in the work list. Next, I keep going in through the work list again. Take B3, its successor is B4. That doesn't satisfy the EBB requirements of unique predecessor, so I don't put B4. So nothing else to be done here. And then B5 I have, and that has no successor, so nothing needs to be done there. So in this particular case, you can see that the extended basic block is what I have circled here, here like that. So it is an acyclic graph. It's really a kind of a tree actually, not even a acyclic graph, I would say. It's a tree, and that does not have any join in it. So you can see that B4 is excluded from it because it had a join. And it's a maximal structure. So if we had something else, maybe from B3 side, the unique predecessor, we would have added that as well. So again, it's a tree which is rooted at a given node. From there, there's no join in it. And there are other basic blocks which are a part of the tree. So first we discover EBB by using this algorithm. Start with the root of the CFG, do this, and be done. Then pick up a node which is not a part of EBB, currently generated EBB, like B4. And we'll see if we can find EBB which is rooted at B4. In this case, B4 will be by itself. So we'll have two EBBs. One is this, and second is just B4. But in general, we could have some successor of B4, which is again a unique successor, and so on. And so we'll find yet another structure. And so union of all these different EBBs, which is what we'll get as our original CFG. So in short, the CFG is split into multiple EBBs, each one being a maximal one. And there's no join being present in any of them. Once we do that, what we do is next is we do the value numbering on each one of them separately. So how do we do it? We start the value numbering in basic block B1, which is the root, following the previous algorithm that we saw in the last lecture. And we will generate a value table, a hash table, and so on for B1. And we'll do elimination of redundancies, if any, within B1. Once we are done with that, we can go to B2. And these tables, whichever we have generated here, like for example, T1 is equal to X plus Y. So you can see that there will be a hash value structure for this, value of X plus value of Y, generating some value for this X plus Y, and that being stored into T1. So these kinds of things will be present, whatever we generated during the value numbering of this basic block. It will be part of the tables, an expression table and a value table for each scalar variables. This will be there. And once then we finish the B1's execution or processing as far as the value numbering is concerned. Next, what we do is, using these tables which are generated in B1, we'll carry out a value numbering in B2. So for example, T2, if it is equal to, let's say x plus y, this is where we'll be using the value table and expression table. So again, you can see that plus, if the value number of x is 1, that is y is 2. This kind of a hash expression and a value number associated with that will be already present in the value table, the hash table for expressions. And when we go to again B2, when we try processing x plus y, again we will be generating plus 1 comma 2 as the hashed expression on the right hand side of this statement. This expression plus 1 2 is same as earlier one, you can see, and they'll get matched, and we will discover that the x plus y in B2 is really same as a certain value which has occurred earlier because of the same value number associated with them. And we'll, again, the way we do it just within a basic block, exactly similar way, we'll find out which is the temporary with which this value number is attached, which will be T1. Number 3, let's say, is the value number for this. That is attached with T1 here when we process this and put it in the value table. So here we'll look it up. When this generates a value number 3, we are going to look it up, find the temporary name, which is T1, and do this T2 equal to T1 optimization there, and keep going and do whatever is possible using the state of this table in a similar way. So at this particular point, we have now generated a table for B1 followed by B2. Next, we'll go to B5 in that particular order. And in B5, we'll again use these two tables which are generated to do the optimizations and removal of redundancies exactly the same way as we saw in the T2 in case of B2. So in short, these value numbering keeps going down from B1 to B2 to B5 as though they were one single basic block, as though it is going down in one single basic block, and getting the trees and the value context for this. We are able to do redundancy removal downhill in B5 and so on. And we are, of course, going to optimize B5 just like we did B2. Again, constant propagation, whatever, algebraic manipulation, exactly everything will go on as though they're in the same basic block. Now at this point, we are done with this chain. So what do we do? At this point, whenever we are done with the value numbering of B5, we will remove its local tables and expose the context from which it came. What is the context? The context will be B1, B2 context. And at this particular point where I'm drawing this arrow, the tables which borrow the context of B1's value numbering followed by B2's value numbering, that will get exposed. If we were to do B4, that is the context that will be used for carrying out value numbering for B4. Of course, B4 is not a part of EBB here, so we don't have to do it. But then next we'll go to B3. And so before we go to B3, we will have to just restore the context of only B1's tables, value tables, B1's expression table and B1's individual hash functions, which is like, for example, T1's value number is 3. These kinds of things, we will, that those two tables and their state, whatever they have, will be exposed. So once we are going down from B1 to B2 and B2 to B3, we were just pushing the corresponding value tables and onto a stack. So for example, we went for B2, we exposed B1's value table at the top of the stack. When we went for B5, we took B2's value table and pushed it on the stack. And then we collectively looked at, in B5's value numbering, we collectively looked at B, the B1, B2, as I have been mentioning. And then once we decided to go to B3, we popped B5, we popped B2's context. In this particular case, B2's context is gone. So therefore, B1's context is exposed here. And that's the one which we use for doing the value numbering of B3. So the stack topmost context is the one which is my predecessor in terms of this value schema. Value schema allows me to sort of borrow the context and do the value numbering. So it is pretty straightforward. By staying within the basic block and by getting the value context of the expressions as well as variables, I'm able to use those to carry out the value numbering in things like B3 and so on. And so as long as I'm within the extended basic blocks, this is very much possible. And that's why this is called as a super local value numbering. And the schemes remain very much similar to the one which I would use in a single basic block. Okay, just have to be sure that the context is maintained properly before I do the volume numbering. In other words, if I'm doing it in B5, the context is B1 must be followed by B2. Whatever that context provides me is where I can go and do the value numbering. It cannot be that, oh, I just do B1 but forget about B2. That is wrong. And the pseudocode for this and so on is very straightforward. Generate EBB, traverse top down in EBB from root to its leaves, and inherit the value context from the parent. And if you are at the leaf node, then you're done. Then you got to unwind all the stack all the way, go to the predecessor, look at its successors, go to the 2 levels of predecessors, look at the successors along that path, which may be relevant in terms of using its context, and keep doing this. So so far the SSA is only allowing us whatever it did in the single assignment scheme. It is telling us what is the most relevant expression that we should be carrying between two nodes based on the SSA, and so that things don't get killed. So that's the role which I had shown earlier, that x plus y is not killed because of usage. So keep that intact in terms of by SSA names, and that way the values are remaining available everywhere in order to substitute freely. That is the value of SSA in value numbering. Any questions about EBB or extended basic block value numbering scheme?
There's nothing in chat about it.
Okay, so if that is the case, then I'm going to resume the discussion, and we will go back to our global. So this is what we just talked about, EBB. And global value numbering is one of those optimizations which you'll see it does a lot of interesting stuff. Like, so in modern compilers which are SSA based, we do the GVN. This is called as popularly called as GVN. To determine the identical expressions and to get rid of redundancy and so on. And it tries to establish a value equivalence and an availability of a expression at a given point. And we are then able to interchange them or use one of them and get rid of the redundancies. So here is the very big key idea, and which is sort of not a big surprise, but the implementation of it through SSA is the interesting one. So what we are talking about is two values or two variables being equivalent at some program point P. Okay. When are they equivalent? They are equivalent provided they are congruent. And that's the definition we have to see what is exactly a congruence. And then their defining assignments dominate the program point P. This is simple. The second part is straightforward and simple. And here is the basis for that. So let me go back and again switch to our whiteboard. So we are, let's say, operating at some program point P here. Okay, and what it says there is this, that whatever definitions we are operating upon, the two definitions that we are operating on dominate this particular program point. So let's say the two definitions could be V1 and V2. These are the two variables whose definitions are we are considering. So they must dominate this program point P. In other words, in SSA terms, they must be the prevalent definitions. If we had to tap into and say, hey, what is this we are considering? And to avoid this, I will just call this as some V1 and some U1. Let's just call this. Okay, because V1, V2 will be V's definitions and U1, U2 will be U's definitions and so on. So we have two distinct variables lexically, let's say V and U, and we have several definitions operating as per SSA at different points. But if we tap into this particular point, these definitions dominate this particular point. And so therefore, they are the prevalent definitions here in terms of which V we are talking about and which U we are talking about. So that means their values are the ones which are currently preceding. Now, how can this be the case? Of course, that could be the case in multiple different ways. We have, particular region in which we have this phi function going on here, which generates V1, and this also another phi function there, which is generating U1. And then they flow here, they are all in this particular region. There's a join here, but there's no phi function. So V and U tend to be dominating this particular point P, And so suppose I have a use of this V1 here. I could throw that away and I could substitute it by the U1. Okay, so that's basically will be going on. The other way it could be is this phi function could be just over here, these p functions rather. They could generate these different definitions right in the block, and this point of their generation, you can see it dominates everything within that block. And so therefore, if I have any kind of region of their prevalence, it would be from this phi point downwards, and we could take one of them and substitute by the other and so on, because they are exactly identical. The value that is seen in V1, okay, if the value is, we call it at a V of V1, and a value that is C in U1, V of U1, they are exactly equal. Now, what if by this second condition that they both dominate a given program point of interest to us? Well, that is a very simple thing to see. If they did not dominate, they will not be prevalent. As simple as that. So suppose this definition was generated somewhere here, V1 was generated here, and it did not dominate this particular thing. So SSA wise, this would be something V3, which will have a phi function, and V1 might be equal to U1, but the prevalent one at this particular point will be V3, not V1. So that is why the domination relation, that both of them must be dominating a given point, because that's an important condition for them to be prevalent. And by both of them being prevalent at this point, the second condition, which is important for the free substitution, is their values must be identical, which is the first condition. So the values must be identical, but that's not sufficient. They must be all simultaneously prevalent also, which is given by the second condition. Now, just because they are simultaneously prevalent, it doesn't mean, of course, that their values are identical, and that's why the conditions together form necessary and sufficient condition that the values are both prevalent at the same program point given by the dominator relation. And of course, they're equal, so therefore they could be substituted freely. So now the question is, how do we find this equality of the values given by extending the global value numbering in the places where we covered the cases of basic block only, which is simple. Then we extended to the extended basic blocks, which did not have join. So let's just clear all of these. So we covered this case, that V1 and U1 are identical in terms of their values and so on, right? We covered the case where we can determine all this by going to EBB. V1 is equal to U1 and so on. So we were able to do so, but we could not tackle this case. This is my phi function and so on. But what if they're equivalent here? How can I find that out? And that's the case which will be tackled through the SSA in a very clean and elegant way. And you will see that. And once we tackle the case of V1 is equal to U1, here the value equivalent case, and they're also, of course, dominating this particular point in the second part of the things. And then we can try to declare them as equivalent and then process it in terms of their substitution and so on. Any questions about this overall setup of how we are dealing with the question of the two being equal in terms of values, and the second fact being we had to check and assertion about is that the both of them have the same value. Questions about that? Okay, if there aren't any, then I think we can move and see how to determine the V1 equal to U1 in terms of the equivalence of values. Okay, so we'll switch back to the. Okay, so again, these are the two conditions. Congruent means they must carry the equal value, and their must be in the dominated region, the place which where we are trying to substitute one by the other and so on. And therefore, these two conditions must be satisfied for doing any transformation. The first condition that they are congruent or they're equal in terms of their values, that is expanded further using the SSA notation and the values, how they are really derived in the SSA format. So look at this, the second bullet of this on this presentation. Two variables are congruent or exactly equal in terms of their values if their definitions have identical operators and congruent operands. And this is the thing which we'll be using to build a relationship of in terms of the SSA and things like that. So I'm going to explain that a little bit using the whiteboard again. I wish this was more in person, but anyhow, we do have electronic whiteboard here. So focus on this, identical operators and congruent operands, okay? These are the keywords you should remember. And we will do so using the SSA format. So okay, back to our original examples, and we'll see how to cast this. P is equal to X, Q is equal to Y, X plus Y, T1, T2 is equal to P plus Q. Boom, boom, boom. Let's do the SSA here first, and then let's do the SSA oriented representations, and then we'll see how to figure this out of equivalence of T1 and T2 using the SSA based notation now. Okay. So we have X, let's say, labeled as X1 here. P is labeled as, let's say, P2. This is labeled as Y2. Let's Q3 be labeled as Q3. I'm randomly selecting these labels. And we have X1 and then Y2, sorry, which is prevalent names of SSA. It's all within a basic block, okay? And then let's just T1 be T1, just a little easier that way. And then we have this P2 and Q3. Okay. So now what we do is we build some nodes here which are carrying the operands or operators. And we will label them as per the equivalence that we are seeing. So we'll first, again, just like in our, what you call it, local value numbering and all these things, what we'll do is we'll build this name, these things which you can think of as value numbers, and we will have a mapping corresponding to the value numbers carried out here. So this node will give it label first of all. If this X1 is not attached to any particular node, this is actually the value which, and this value X1 is given as a label to this particular node. Think of this value being assigned to the value number. Now P2 is of course same as X1, and so this is also P2. Carries the this particular node carries the same label, which is X1 and P2. Similarly, Y2 and Q3 will get assigned to this. Now, what we'll do is to synthesize an expression value, we will first do exactly similar as locate the node, which is corresponding to the value. So this is that value, and this is the node corresponding to that value, XV's value, X1's value. And we will put an arrow from there because we are taking that value, and we are taking another value here, okay? And you can see that we will put a plus operand here. Just like it's just a different notation. We were doing the same thing through the hash expressions. Now we are doing it through this particular graph. That's about it. Okay. Now, one other difference we'll have here is, remember the first operand here is X1. The second operand here is Y2. So we will have given these labels to the edges because we want to give them a positional correspondence. So in other words, X divided by Y and Y divided by X are very different. So they are not commutative operators. And we have to distinguish between the positions of the operands. So the first operand is given label 1 and label 2 for the second operand on the other edge. Now this is generating another new value, this plus. Now what is that value assigned to? T1. So T1 is basically given this, okay, this particular label. And in a similar way, what we would do is for representing P2 plus Q3, if we do the same kind of thing, it will generate something like this. We'll connect the first edge here. We'll connect the second edge there, right? First operand is P2, second operand is Q3. These two nodes are there. And we'll have a plus here for that, and this T2. This particular graph that we have generated is basically called as value graph. How is it generated again? We start with the values. If they don't have any node associated with them, the value must have a node associated with them, okay? If this X1 doesn't have a node associated, we'll put that node association to the value to that node. Now, if that value is assigned to some other value, not only X1 will have a label to that value, but P2, because they are the same value, they will get assigned like this, Y2 and Q3. Okay. Now comes to processing expressions like these, we will take the first operand, find out the node label for that, right? And then we will connect that node by plus value to the plus node to do x1, and this node y2 to this particular node T1, and this correspondingly arrange 1 and 2 as the labels of the respective edges. First operand given 1, second operand given 2. P2 similarly, go to that node and then connect it like that. Okay. Now we want to verify if T1 and T2 is congruent. Okay. What is congruence? Congruence means whether they will always bear the same exact value or not. How do we do that? First of all, we check the operators from which they are synthesized. So this is, both of them are plus. That's the first test. So that first test is passed. Second test is the respective operands on their corresponding edges be congruent or identical. So what is the first, this T1's first edge operand? It goes to this particular label, and that is P2. Sorry, that is X1. Okay. So it corresponds to this label. And T2's first operand is P2. Now the question is, are they congruent? Since they are referring to the same node, they are congruent. Okay. Because they are bearing the exact same value. And in a similar way, if we take the second operand of T1, what is the second operand of T1? It is Y2. And what is the second operand of T2? It is Q3. The question is, are they congruent? The answer is yes, they are congruent because they are referring to the same node. So if the operators are the same, if the first edges, the operands, respective operands on the first edges, if they are congruent, X1 and P2 are congruent because referring to the same label, same node, and Y2 and Q3 are also congruent referring to the same node, all these conditions are satisfied, and that basically means T1 and T2 are congruent. Okay, now extending this here, I just want to kind of quickly show you how this process really works. And so this is my plus, and this is my T1. This is my plus, and this is my T2. And I'm just going to draw something here because it's a little cluttered here. Extend this further. And let's say there is a division operand here. This is 1, this is 2, this is 1, and this is 2. And these two are the now the nodes which are let's say something like 5 constant here, constant 5 here. So and now let this be T3 and this be T4. Now the next question I might ask is T3 and T4 congruent? In order to answer that, again what I do is I do exact same thing. I start with the operators. Check those. They are the same operator. Test 1 is passed. If these two are different operators, to begin with, they are not congruent. Okay, for example, if this is division and this is multiplication, or this is division and this is subtraction, or that is plus and this is minus, if there are two different operators, they cannot really generate the results which are identical, right? So that's the first cut. But in this case, both are division, thankfully. Next, what we'll do is we'll go on the edge 1 here and edge 1 here. And we'll ask ourselves a question, is T1 on my edge 1 and T2 on my edge 1, are they congruent? And for that matter, I would go here further in this graph and verify the T1's and T2's congruence by going to their respective edges. Again, whatever we did earlier, we would try to process that going on with X1 and P2 congruent, for example, because of these both going on their edge number 1. And because they are labels of the same node, they must be congruent. We'll determine that Y2 and Q3 are congruent again. So we would have checked number 2 operands congruent, number 1 congruent, their pluses being congruent. Again, we will declare T1 and T2 congruent. So we pass this check here. Now we'd go to the question H2. We still aren't done. In terms of T3, the second operand is a constant 5. In terms of T4, the second operand is also constant 5. And the node labels here again are identical, 5, and they bear the same value, which is a constant value 5. So these are also identical, and therefore T4 and T3 and T4 are congruent. That's what we will declare. So in short, if we build this particular SSA graph through the whole program, that tells us how each one of the SSA values is synthesized, from which are the constituents from where it gets synthesized. If the constituents are identical, then the resulting SSA values are identical. That's what this particular simple algorithm says. And so it first builds a value graph, like this big graph with 3 levels here, for example, and even more, as you will see through the other example. And then it walks it whenever we want to prove a pair sort of congruent. It will check if their operators are first, like in this case, division and division are congruent. If they're not congruent to begin with, they're obviously, those two values will not be identical ever. We will not worry going further down. But if they are, the operators are the same, they are congruent there, then the next thing that we will check is go on the respective edges, check their respective operands are congruent, and keep going down and verify the congruence. And if at every level we are able to prove them to be congruent, then the original constituents T3 and T4 will be congruent. So that's the general nature of the SSA-based global value numbering algorithm. Again, what is being built here is a value graph which is global, and we are leveraging the fact that if the two values are exactly identical, their value numbers are identical, and therefore they become the labels of the same node. That is the key starting point of the algorithm. The one is, of course, being the copies of like these I mentioned. The second one could be these, the two nodes are constants, and so their labels are identical because the values are the constants themselves. And with those two starting points, we'll build this relation. You can see that here T1 and T2 we built as identical, and then did some further operation, T1 divided by 5 and T2 divided by 5, and that declared the resulting values T3 and T4 as identical, and so on. So this is the way the equivalence will be proved in the global sense by using the SSA names. Again, equivalence means they will exactly have the same values. Now, whether those both exact same values prevail at a given point or not is controlled by the second dominator check, And if that check passes, then obviously both the values are prevalent at that point, and we will be able to remove one and put the other interchangeably. We can use them completely interchangeably because they are proved to be exactly equal there and also prevail at the same time. And that's the nature of global value numbering. Any questions?
Nothing on chat.
All right. So before I switch back to the main slide, because I'm doing too much switching, I will just illustrate one other fine print here. And that should be pretty obvious, but it's still an important part. And then we will switch to the main part. Okay. All right. So now I told you we are worrying about how these values are getting synthesized in our framework. And this is SSA. So the operators that we covered so far are, of course, the important ones: plus, minus, star, and arithmetic operators coming from the IR, from the arithmetic instruction set of this, division, compare, whatever, and or all these operators. But that's not all. As you know, we have a major operator which is not covered yet, which is the phi function. So the SSA values are not only synthesized by using this plus, minus, and all the other things, but they're also synthesized by phi functions. And we must cover that in order to complete the discussion on the GVN, or the value graph. So what is going on here, and how do we note this particular aspect? So consider a basic block. Okay, consider a basic block and certain values coming into that basic block along the two edges, and we have a SSA phi function here for x, x1, x2, and we have another phi function for y1, y2. Okay, x1 and y1 come from this one, x2 and y2 come from this one. So now to preserve this x3 and y3's equivalence, which is what I'm going to draw here, x3 and y3, we must look at this particular phi function and infer the equivalence using this phi function. So this is my phi function phi. This is my phi function phi. Okay. And this phi function for x1 now operates on this x1 and this x2 and this y1 and this y2. So we'll extend this GVN in this particular way that x3 and y3 are equivalent, okay, provided their underlying phi functions are equivalent. And note this particular fact, because this is really important, that this phi function and that phi function must be identical. Number one condition. And the fact that, let's call this as edge 1 here, on which x1, y1 is coming, and this is h2, x2, y2 is coming. So this is my edge 1, which is labeled here accordingly as operand 1. And operand 2 is what? x2, y2, which is coming from the other edge. So in order for x3 and y3 to be equivalent, x1 and y1 must be congruent. Okay. And x2 and y2 must be congruent. Okay. So what it means is this, that in simple intuitive terms, two congruent values are coming, x2 and y2. I have a pick of one of the two. and the SSA gets one of the edges, so that choice continues at the x3 y3 level because of that reason. Okay, that's what it means here. And similarly, x1 y1 are congruent values. They have equivalent, they are exactly same values. Let's just use a simple term. They're exactly same values. And so I could use them interchangeably. Both are admitted when the edge one is of the flow graph is switched on by the gating function because the control is coming via there. So I continue to again choose between x1 and y1, and that is reflected again in x3, y3. So x1 and y1 are admitted. That continues x3 and y3 to be identical, and or x2 and y2 are admitted at the same time when the edge 2 is switched on, and again that leads to x3 and y3 being identical in terms of the values. That is what is shown and understood by this particular flow graph. So if, for example, x1 and y1 were to be identical in terms of values, but x2 and y2 were not. So for example, operand, this operator passes the test. This operand side also passes the test that the x1 and y1 are identical, but x2 and y2 are not. That basically will invalidate the x3 and y3s being identical, because whenever the control comes h2, we'll have x2 and y2 which are not identical, which leads to x3 and y3 not being identical. So the sufficient condition for x3 and y3 to be identical is that x1 must be identical to y1 and x2 must be identical to y2 on the respective edges. And that is exactly the condition which we had earlier also. So in short, this, regardless of the operators, plus, minus, division, this, it also extends this to the SSA phi functions. Now I told you that the underlying phi functions here must be identical. What does that mean? That basically means that we must be getting it at the same basic block. And so what we do now is call the gating function at a given basic block by unique name. So I have this particular basic gating function at the basic block 1, let's say. I'm going to call this as phi1 here. These will be phi1 because they are in basic block 1. For gating function with the x, for which may be for x, but which is for another basic block 2, I will call this gating function as phi2. And so whatever gating is happening between x1 and x2 here in 2, that will occur at phi2. And it will have constituents x1 and x2. Okay, got it? So where the gating occurs is really important, because that is exactly what is going on. The values are flowing into a given basic block by the prevalent gating function there, which will be phi1 in basic block 1 and phi2 in basic block 2. So we must distinguish between these gating functions also based on the basic blocks, and therefore we will so far we will just calling this as phi of x, x1, x2, and we were not localizing it to a given basic block. But for this particular purpose, it is important to track the basic block into the values which we are coming there. And so we will call these gating function as phi1 for basic block 1, phi2 for basic block 2, and so on. Okay, so all the gating functions for basic will be called as phi1 of x1, x2, phi1 of y1, y2, and so on. And that's how we will note that this phi1 and phi1 are the same gating function for the same block, with the same x1 being identical to y1 and x2 being identical to y2. And that completes the equivalence of, or the equal values of x3 and y3. For a different basic block, we will use phi2 And then again, similarly, we will find out if the corresponding operands are identical or not, and the underlying phi2s are identical or not. So it is important to distinguish the gating functions for these reasons, because they are showing different flow of values at different program points, and that flow is the one which is important for the equivalence of the resulting X3Y3. X3 is synthesized out of phi1 and not out of phi2, and that is important to be tracked. Is there any question about this part? Okay, so looks like we are ready then go to our original discussion here, and now we'll complete the the discussion. So let us see how we do go, having understood this deep core and the basic algorithm. How is it's very easy to see how we find these. So the nodes are again labeled with operators, functions, whatever constant values as I named. The nodes are named using SSA variables. That is another thing that we already saw. And then from operators or function, these are there are directed edges to operands. That's also we saw. And the edges are, of course, positional in terms of numbering 1, 2, 3, 4, like first operand, second operand. So this leads to the value graph. Now, the two nodes of the value graph are congruent or bear the exact same value. If they're the same node, or their labels are constants and constants have the same value, or their labels of same operator and their operands are congruent, which are all the cases which we saw. So how does the algorithm work? The algorithm first partitions the node into congruent sets. The initial partition is optimistic. Okay, and this is another small wrinkle here which I haven't covered so far, but you will see in the example. So the same operator and other things, function name, we are going to put all of these together. They are all equivalent. And the important reason for doing this is, again, just like in SCCP, the fixed point that is generated by this particular solution is an optimistic fixed point, and it is actually declaring many values to be congruent. If we started in the pessimistic sense, we will not be able to declare them as congruent. So the optimistic representation is important, because finally the partition that we are left with is also optimistic as a result of this. In other words, there are 4 pluses in our value graph. We'll all start with the assumption they're all congruent to each other. We could also assume that all 4 pluses are different, and they will converge to different solution, which will not be we want here optimistic solution. We want to declare them congruent if we can as much, because then we can get rid of the redundancies. So starting with the optimistic partition, what we do is we'll iterate to a fixed point, splitting partitions when the operands are proved to be non-congruent. Okay, and we can do this in any order and propagate it, and when there is no change, we can stop it. So here is an example of an original flow graph, deliberately introduced redundancy. You can see here between I and j through and through, starting with they bearing the same value as constants, and they being modified exactly the same way. We have one terminating condition based on j, and second is on I, but doesn't matter. If they are congruent, both terminating conditions are identical, and then all kinds of in-between phi functions will get introduced and will be forced to prove the congruence. So let's see what happens here. So when we convert these into SSA using our whatever we have learned so far, we have I1, J1 there sitting at the top. Then you can see that we have a phi function for I, which is bringing in some values at the bottom and merging it to to produce I3 out of I1, I2. Similarly, J3 out of J1, J2. Then I3 is prevalent. We have a mod condition there for a branch. We are going on left side. From I3, we are synthesizing I4, then J4, and similarly I5, J5, and then we have a phi function at the bottom, join I4, I5, and J4, J5, and then J's condition, and that's basically how the SSA looks like, which should be straightforward to understand. And then from this SSA is what we are going to generate as the value graph by putting all these nodes. And notice now that phi2 here, remember, is I told you that this is a phi function which is for a basic block B2. So we call this as phi2 and this as phi5. We could have simply left them as phi of whatever I1, I2 and phi of I4, I5, but it will not be right for the purposes of doing GVN. So these are the functions which are getting in two different basic blocks, and we must separate them using the nomenclature that this is a gating which occurs in B2. And so when we are proving equivalence, we are going to gate it using this function. And when we are proving equivalence there, we are going to gate it using another function. And there's no way phi2 and phi5 are the same function because they are operating in two different basic blocks. So note this important point. But given this and the SSA, now the rest is very easy. So using this, whatever we discussed earlier, we form this particular graph, value graph, and you can see that this has come out to be for getting all these I values, and then the bottom one is for the J values, which are getting synthesized again from these constants and so on. Now, if you apply this algorithm here and work out through some details, first of all, you will put these pluses, all four pluses, I4, I5, J4, J5, in the same equivalence class, and then we'll iterate and prove that here in this particular case, I4 and J4 will be equivalent, I3 and J3 will be equivalent, and J5 and I5 will be equivalent, and J2 and I2 will be equivalent. So we'll separate them out into these four classes by iterating things like that. For example, if you just consider though they are both corresponding to, so it's easy to see why I5 and J5, J5 and I4, J4 and I4 are equivalent because their operand number 2 is constant 1, operand number 1 is 3, I3 and J, and I3 and J3 are equivalent. Therefore, I4 and J4 are equivalent. However, J4 and J5 are not equivalent. It's easy to also see that because their operand number 1, although it is the same, J3, operand number 2 is going to 3 in case of J5, and in case of J4 it is going to 1, and therefore they are distinguished based on their operand number 2, which are two different constants. So that's how partitions will get split, and some partitions will remain the same, and that's how the algorithm will converge. And because of optimism, you can see that we will be able to keep I4 and J4 together because their being together depends on I3 and J3. Now I3 and J3's being together, in turns you can see that it depends on J1 and I1, which is just fine. but the other operand is J2 and I2. So it depends on they being together. Now, if you go to J2 and I2's being together, again, in turn, it depends on J4 and I4 being together, right? Because they are there. Look at J2 and I2. Their number one edge depends on I4 and J4. So it's a transitive closure here. You can see that I4 and J4 being together depends on J3. That in turn depends on J2, and J2 in turn depends back on J4. So if you do partition in an optimistic sense, and if you separate them out, there is no way you can prove the partition to be I4 and J4. Try splitting it and separating it out, I2 and J2 and I3 and J3 in separate parts to begin with. Or rather I5 and J5 in separate parts, and you will see that you will not be able to keep the partition as um, um, as the way it is actually found. So in other words, we should start with all I5, all four I4, J4, I5, J5 being together, and then split it off. So that's what is covered here, especially this particular part. And if we introduce a minus or something in between, you will see that this particular I5, if it is separated out from J5 because of minus, then it will split off, and it will also split other stuff out, because if I5 and J5 are not the same, then you can see J2 and I2 will not be the same, and in turn the I4 and J4 will also not be the same, because of I3 and J3 may not be the same. Okay, so that's what is explained here, and so this is GVN. I will stop here, and again, what is the essence of it? The essence of it is being able to build this global value graph, incorporating the different phi functions labels here across different basic blocks, and verifying that in order for two operands to be congruent, their constituents must be congruent on respective edges, and their operand must be the same, their operator must be the same. And we start in an optimistic manner, that is all four here, I4, I5, J4, J5 being all identical, and then we will undertake the split here, and that leads to an optimistic solution, which is I4 and J4 are congruent, and so on. So that's an important part. Verify the optimistic part and try doing it without the optimistic part, and you'll see that you will not be able to achieve this, especially because of the transitive nature of this dependence here, which is violated if you keep them separate and not equivalent. So when we separate them out, only when we are proved that they must be separated, otherwise we keep them, and that leads to an optimistic solution. So that is how we declare things to be equivalent at different points. And if you see this, we'll have I2 and J2 and so on as equivalent at different points, and therefore one of the values is totally redundant and can be eliminated from everywhere, and we can carry out SSA-based optimizations of getting rid of the redundancies, things like that. For example, I3 plus 3 is same as I5 and J5 are the same, so you can get rid of one of the two operations and so on. So let me stop here. I guess we'll have office hours. So we won't have a class on Wednesday, on coming Wednesday, because of the school holiday. So take some break, relax, We will have only one homework after this, which will be lightweight. And we have already given the term paper and the project. If you have any questions or any of them, we will be, of course, responding over Piazza. So have a little bit of break and relax, and we'll talk to you again. Thank you. Next week on Monday. Bye-bye now.